Welcome to the deep dive. So today we're taking a bit of a fascinating and I'll admit often challenging detour. We're jumping right into the complex world of statistical bioinformatics.
It's a big topic.
It is. Our mission here is to really understand the crucial analytical shortcuts scientists have to use when they're faced with these impossibly large data sets. We're talking specifically about gene expression data with thousands and thousands of variables.
Yeah, and it's a classic scientific bottleneck, How do you stop yourself from finding just an endless stream of false positives when you're running thousands of tests all at the same time?
Right.
So to tackle this, researchers have really relied heavily on two major approaches. There are the resampling-based methods and then the more modern, really powerful empirical-based methods. We're going to get into both.
Okay, and to ground this, because this is a massive topic, we're going to use one of the most famous data sets in the history of cancer genomics. It's the gene expression data from Golub and his colleagues back in 1999.
A landmark paper.
It really was. This data was so pivotal because it used microarrays to define different subtypes of leukemia, and it really showed the power of these new statistical techniques.
And its structure is just a perfect illustration of the central problem we're talking about.
Yeah.
The version we're looking at is a pre-processed training set, and it has this massive dimensional imbalance.
What do you mean by that?
Well, you have 3051 genes. Those are our variables, right, organized in the rows.
Okay.
But we're only working with data from 38 tumor patients. That's it, 38 columns.
38. Okay, let's unpack the specifics of those 38 patients then. The core nuggets of information here, they include the normalized expression values and really crucially, the group membership. That clinical variable, it tells us we're comparing two very distinct groups of leukemia. 27 patients with what's called ALL, acute lymphoblastic leukemia, and then 11 patients with AML, or acute myeloid leukemia.
So there you have it. Thousands of potential predictors, the genes, and just this tiny handful of samples of patients.
This is exactly where the core challenge hits. If you're comparing two groups, ALL versus AML, across more than 3,000 different genes, why can't we just run a standard t-test for each gene on its own? What makes the scale here so, statistically treacherous?
The scale itself is the problem. I mean, think about it. If you set your significance threshold, your alpha, the standard 0.05.
The 5% rule that everyone learns.
Exactly, the 5% rule. You are essentially accepting that 5% of your tests will come up as false positives purely by chance.
Just random luck.
Purely by chance. So if you run 3,051 tests, even if absolutely none of those genes are truly different between ALL and AML, you are mathematically guaranteed to find over 150 genes that look significant.
Wow.
But they're completely meaningless.
That's actually terrifying for a researcher. You've just discovered 150 genes that could send you down a complete scientific dead end for years.
It happens. So we have to have a mechanism that manages that error across the entire experiment, not just gene by gene. And this led to a really pragmatic, kind of paradigm-shifting change in statistical thinking for high-throughput biology. We stopped chasing the traditional p-value for each test and started controlling the expected proportion of error across the whole study.
Which is the false discovery rate.
Which is the false discovery rate, or FDR, exactly.
So the FDR, it doesn't guarantee that every single positive discovery is true. Instead, it controls the expected proportion of false positives in your final list of genes you call significant. It's like you're building an error budget for your entire discovery set.
That is the core insight. That's a great way to put it. And this shift was so fundamental that it necessitated whole new statistical methods. People have done comprehensive comparisons on this, showing that traditional methods just completely fell apart under this massive variable load.
And that brings us to our first solution category, right? The resampling-based methods. The most famous example here, I think, is significance analysis of microarrays, or SAM. So how does SAM use this idea of permutation to solve that multiple testing problem?
SAM is. Yeah. It's really elegant because it kind of bypasses complex mathematical distributions by just using pure computation. It's a permutation-based method, and what it does is create a synthetic null universe.
A null universe.
Yeah. It takes your clinical labels, the AL and the AML, and it just randomly shuffles them thousands and thousands of times. By doing that, it generates thousands of random data sets where the labels are totally meaningless.
So it creates a world where we know for a fact that no gene should be significant.
Exactly. So for every single gene, SAM compares the score it got in the real correctly labeled data to the distribution of scores it got in those thousands of randomly labeled, null data sets.
Okay, I see.
By comparing your observed results against this null distribution of meaningless results, SAM effectively estimates how likely it is that any difference you saw is just a false positive. And that probability, that's how it calculates the FDR within its framework.
That makes perfect sense conceptually. It's actually incredible that raw computation can solve a problem that traditional statistics really struggled with. But let's move from the concept to the actual application. If I have the Golub data, what are the steps to actually run a SAM analysis?
Well, the implementation, it does require some specific syntax, but conceptually it's pretty straightforward. You need 3 key inputs. First, obviously, the massive gene expression matrix itself.
Right.
Second, the clinical labels, so ALL versus AML. And third, you need to tell the system that the data has already been prepared, specifically that it's been log transformed.
Got it.
Once you assemble those pieces, you just tell the function that you're performing a comparison between 2 distinct, non-overlapping groups, the 2-class unpaired analysis.
And then the computer just cranks through the thousands of permutations. But the job isn't done, is it? Because the output is just a big list of genes with all these associated FDR estimates. The critical and kind of subjective choice comes next.
Yes.
And that's selecting the parameter delta. This value acts as a kind of gatekeeper.
This is really where the statistical math meets the researcher's actual strategy.
Yeah.
Running SAM gives you a table. It shows you all these different possible delta values and the corresponding FDR you would get at that threshold. You have to select a delta that balances discovery power with acceptable error control.
And the goal, in a lot of major studies, is to pick a delta so that your resulting FDR is 0.05, that 5% again. But here's where it gets really interesting, because the calculation of that FDR can be more or less stringent.
Yes.
You can base it on the median of the FDR distribution, or you can go more conservative and use the 90% quantile.
And this is a fundamental strategic choice. It really dictates how certain you want to be about your results. You can think of it like a quality control guarantee on your list of significant genes.
Give us an analogy for that. What's the real difference between using the median versus the 90% quantile?
Okay, so if you choose the median, you're basically saying, on average, my false discovery rate will be about 5%. Half the time it might be 3%, and half the time it could be 7%. It gives you a wider list of potential discoveries, but with a bit less certainty for any individual gene on that list.
A bigger net, but maybe some holes in it?
A bigger net, exactly. Now, if you choose the 90% quantile, you're building in this massive safety margin. You are assuring that 90% of the time, your error rate will be at or below 5%. So you're sacrificing some potential discoveries for guaranteed reliability. It is a much, much more stringent, much more conservative approach.
And in the source material we're looking at, the analysts working with the Golub data, they chose that conservative route.
That's right. They settled on a threshold value of delta equals 1.11.
1.11.
And that specific delta was chosen precisely because it corresponds to that more conservative approach, where the 90% quantile of the FDR is 0.05. That is the gatekeeper value that defines the final, highly reliable set of significant genes distinguishing AL from AML.
Okay, so we've got SAM, which relies on this brute force shuffling. It makes the process clear, but it also kind of raises a point against these resampling methods, doesn't it?
Yeah.
Relying on shuffling thousands of times sounds incredibly computationally expensive.
It can be.
Especially as gene counts grow way past 3,000. So what is the major drawback of permutation? And did this lead researchers to look for faster, maybe alternative methods?
That's an excellent point. The computational load is definitely a limitation. Another thing is that the stability can sometimes be an issue, especially if you have very small samples, because the results do depend on those random permutations.
Right.
This need for speed and stability is exactly what drove the field toward that second major category of methods we mentioned earlier. Empirical Bayes.
Okay, so let's pivot to empirical Bayes. The most common implementation of this method is in a package called LIMMA. I think that stands for Linear Models for Microarray Data.
That's the one.
How does empirical Bayes tackle a problem differently than SAM's permutation approach?
Empirical Bayes is. It's conceptually brilliant. In standard statistics, like we said, when you only have 38 patients, your estimate of the variance, the variability of gene expression for any single gene, is inherently unstable. It's unreliable.
There's not enough data.
Not enough data points. So empirical Bayes solves this by, and this is the key phrase, borrowing strength across all the genes.
Borrowing strength. What does that mean in practical terms?
It means that instead of relying only on the 38 data points for, let's say, gene X, to calculate its variance.
Okay.
The method uses the information from the other 3,050 genes to inform and stabilize the estimate for that one gene, gene X. It assumes that while all the genes are different, they share some common underlying distribution of variance.
So it smooths out the weirdness from any one gene by looking at the bigger picture of all the genes?
Exactly. By shrinking the variance estimate for each individual gene toward this common shared distribution, you get a much more robust and reliable statistic at the end, especially in small samples.
That's a fundamentally different way of thinking about it. So SAM uses simulation and shuffling to estimate the error distribution, while Lemma, using empirical Bayes, uses information sharing across the whole data set to make sure the underlying calculations are stable enough to even run the test correctly in the first place.
Precisely. Empirical Bayes methods are significantly faster than permutation methods, and honestly, they're often preferred today because they produce more stable results in studies with limited patient numbers, which, as you can imagine, is very common in early-stage clinical research.
So we've covered the complexity of scale, the absolute necessity of the false discovery rate, the robustness of permutation methods like SAM, and now the efficiency and stability of empirical Bayes methods like Lemma. This really demonstrates that navigating gene expression data isn't just about applying one standard test. It's about choosing the correct strategic tool for the job.
Absolutely.
Uh-huh.
And if we connect this to the bigger picture, the entire movement from unadjusted p-values to sophisticated controlled error rates, whether you do that through permutation or through empirical Bayes, that's the difference between finding noise and finding biological truth.
Right.
And the choice you have to make, between using a median or a 90% quantile for your delta threshold,
Right.
that shows that even once the method is chosen, the final set of discoveries involves a conscious, methodical decision about what level of risk you're willing to accept.
The Golub dataset, it helped redefine our understanding of leukemia subtypes because these methods allowed researchers to confidently say these are the genes that matter. Now that we've seen how a single threshold, that stringent delta of 1.11, can define the entire set of significant genes, here's a final provocative thought for you to carry forward. What variables beyond the purely statistical measures of the FDR? I'm thinking about things like the cost of following up on a discovery, or the availability of existing drug targets for some of those genes, or even the ethical mandate to find any possible lead for a very rare disease, might compel a researcher to choose a slightly less or maybe even a more stringent delta threshold in their next study. The method is math, but at the end of the day, the application is strategy.